Welcome to Copilot Podcasts. What if I told you that the shape of our entire universe might be encoded in tiny mathematical objects we can't even see?
That's actually not as far-fetched as it sounds. These mathematical objects, called spinors, are revealing some mind-bending secrets about our cosmos.
Today, we're diving into Bishopian modular spinors and how they're completely changing our understanding of galaxy formation.
And trust me, what we're learning is challenging everything we thought we knew about how the universe works.
So let's start with the basics. What exactly are spinors, and why should we care about them?
Well, spinors are these fascinating mathematical objects that help us describe how things rotate in space. Think of them as the DNA of spatial movement.
DNA of spatial movement? That's quite a metaphor.
Recent research shows they're actually crucial for understanding how space itself curves and bends, especially in the presence of massive objects like galaxies.
And this is where things get really interesting, right? Because it connects to some pretty groundbreaking discoveries.
Exactly. According to recent papers, these spinor structures are showing us that galaxies might form in ways we never expected.
Wait, how do mathematical objects tell us anything about actual galaxy formation?
Well, there's this fascinating concept called modular fluctuations that Valinde and Zurek have been studying.
Modular fluctuations? That sounds complex.
It's actually quite elegant. These fluctuations show up in what we call causal diamonds, regions of space-time that are causally connected.
And what are they telling us?
They're showing us that quantum gravity effects might be observable at much larger scales than we thought possible.
That's huge. But how does this connect to actual galaxies we can see?
This is where it gets really exciting. The James Webb Space Telescope has been making observations that seem to support these mathematical predictions.
Really? What kind of observations?
They're finding that the oldest galaxies in the universe are much larger and brighter than our traditional theories predicted.
And this wasn't what scientists expected at all, right?
Not at all. The standard model suggested galaxies should have started small and grown gradually over time.
But that's not what we're seeing?
No, and this is where Bishopian modular spinors come in. They might explain why galaxies formed so quickly.
How so?
These spinor structures suggest that space itself might have properties that accelerate galaxy formation.
That's fascinating. But doesn't this contradict what we thought we knew about dark matter?
Yes, and that's what makes this so revolutionary. It suggests we might need to fundamentally rethink our understanding of gravity.
You mentioned quantum gravity earlier. How does that fit in?
Recent work by Alsma and Bach shows that these quantum effects might actually be observable in cosmological measurements.
That seems counterintuitive. Aren't quantum effects supposed to be tiny?
Normally, yes, but their research suggests these effects can be enhanced far beyond the Planck scale.
And this enhancement could explain what we're seeing with galaxies?
Exactly. The mathematics of spinors predicts exactly the kind of rapid galaxy formation we're observing.
Let's talk about these observations more specifically. What are we actually seeing?
According to recent data from the James Webb Telescope, some of the oldest galaxies are unexpectedly large and bright.
And this wasn't supposed to happen according to conventional theories?
No, traditional models predicted these early galaxies would be small and faint, gradually growing over billions of years.
So what does this mean for our understanding of the universe?
It suggests that gravity might behave differently than we thought, especially at large scales.
Different how?
Well, there's this alternative theory called modified Newtonian dynamics, or MOND, that might explain what we're seeing.
And how does that connect to spinors?
The mathematics of Bishopian modular spinors actually aligns really well with MOND's predictions about gravity.
That's quite a connection. But what about dark matter? Where does it fit in?
That's the revolutionary part. These theories suggest we might not need dark matter to explain galaxy formation at all.
That would be a huge shift in our understanding of the cosmos.
It really would be. And it all comes back to these mathematical structures we started talking about.
The spinors?
Yes, they're showing us that the universe might be much more interconnected than we thought.
How so?
Well, these spinor structures suggest that space itself might have properties that guide galaxy formation.
Almost like the universe has a built-in blueprint?
Exactly. And these mathematical structures might be our way of reading that blueprint.
This is mind-bending stuff. What are the implications for future research?
Well, it opens up entirely new ways of studying galaxy formation and evolution.
And I imagine the James Webb Telescope will keep providing new data?
Absolutely. We're just at the beginning of understanding how these mathematical structures shape our universe.
It's amazing how abstract math can tell us so much about reality.
That's the beauty of physics. The mathematics often reveals deeper truths about our universe.
So what's next in this field?
Researchers are working on new ways to test these theories using upcoming telescope observations.
It sounds like we're on the verge of some major breakthroughs.
We really are. The next few years could completely transform our understanding of galaxy formation.
Well, this has been absolutely fascinating. Any final thoughts?
Just that sometimes the most abstract mathematics can lead us to the most concrete truths about our universe.
And that's what makes science so amazing. The constant discovery of new connections and patterns.
Exactly. The universe keeps surprising us with its elegant mathematical structure.
Well, that's all for today on Copilot Podcasts. Remember, the next time you look at the stars, you're seeing math in action.
And maybe, just maybe, those tiny spinors are showing us the way to understanding it all.